March 2018, Kenya. Eliud Njoroge woke up on the edge of an abyss that didn't exist when he went to sleep. A 20-foot wide crack had torn through his farm overnight, not gradually, in hours, swallowing sections of highway, splitting his property in half, leaving his house perched on the lip of a geological wound that appeared faster than anyone thought possible. This wasn't a sinkhole. This wasn't an earthquake. This was the African continent physically ripping itself in two, and it happened so fast that scientists are now questioning everything they thought they knew about how continents break apart. The crack stretched for miles. The ground didn't shake. It just opened. And when geologists arrived to measure it, they found something terrifying. This wasn't an isolated event. It was a symptom of something far larger, far older, and actively accelerating. Hit that subscribe button. This goes deeper than any documentary you've seen. You'll be back for the next one. Don't gamble on finding this again. Lock it in. Right now, at this exact moment, Africa is tearing itself in half. Not metaphorically, not in some distant geological future you'll never see. It's happening now, measurable in millimeters per year, visible in satellite data, violent enough that entire regions are being evacuated as new fissures appear. The Somalian plate is pulling away from the Nubian plate at 7 millimeters per year. In Ethiopia's Afar Triangle, the only place on Earth where a mid-ocean ridge is exposed on dry land, a 60-kilometer fissure opened in 10 days in 2005, releasing 2.5 cubic kilometers of magma and proving that what should take millennia can happen in a geological eye blink. And beneath it all, 3,000 kilometers down, there's a blob, the African Superplume, a continent-sized mass of superheated mantle rock pushing up like a blowtorch aimed at the lithosphere, driving the surface apart with forces that started before dinosaurs existed and won't stop until the continent is completely split. We're going to discover why a geological microplate the size of Germany is rotating counterclockwise between two separating continents like a massive stone gear caught in a planetary machine. We're going to examine lakes that kill without warning, invisible clouds of carbon dioxide that suffocate entire villages in their sleep, a threat currently sitting beneath 2 million people. We're going to visit places so extreme that life itself can't survive. Acid pools with negative pH, lakes that turn animals to stone, landscapes forming under conditions Earth hasn't seen since its early history. And we're going to trace this back to natural nuclear reactors that ran themselves 2 billion years ago, and monuments carved from volcanic rock that the same forces created. The continent is splitting. The ocean is coming. And what's happening right now in East Africa is rewriting everything we thought we knew about how planets break themselves apart. March 2018. Eliud Njoroge heard a sound he couldn't identify, a deep grinding, like the earth was tearing its own skin. He lived in Mayahu, a town in Kenya's Rift Valley, where the ground had always been solid, predictable, ancestral. His home sat on land his family had farmed for 3 generations. That night, the land decided it was done waiting. When the sun rose, a fissure 20 feet wide and several miles long had split the highway in half, swallowed entire sections of his property, and left his house perched on the edge of a new geological abyss. The crack wasn't gradual. It appeared in hours, triggered by heavy rains, yes, but powered by something far older and far more violent. The African continent was physically ripping itself apart, and Riftogenesis, the birth of a new rift valley, was no longer a theory whispered in geology departments. It was happening in real time. The Mayahu fissure wasn't unique. Similar cracks had appeared across Kenya, Ethiopia, and Tanzania over the preceding decade, each one a symptom of the same underlying mechanism, the East African Rift System, a 3,000-mile-long fracture zone where tectonic shifting is pulling the African continent into 2 separate lithospheric plates. The Nubian plate to the west, the Somalian plate to the east. Between them, a widening chasm that grows at roughly 6 to 7 millimeters per year, slower than your fingernails grow, but geologically, catastrophically fast. Scientists had predicted this for decades. The 2005 Dabahu fissure eruption in Ethiopia's Afar region opened a 35-mile-long crack in just days, releasing magma and toxic gases in a violent rehearsal of what's coming. But Mayahu was different. It happened in a populated area. It destroyed infrastructure. It forced the world to confront a question most had dismissed as distant science fiction. What happens when a continent splits in two during our lifetimes? The fracture at Mayahu revealed something chilling beneath the soil. Layers of volcanic ash, ancient sediment and fractured bedrock that showed this wasn't the first time the Earth had tried this. The Rift Valley is geologically young, only about 25 million years old, but it sits atop a much older wound. Deep beneath Eliud's farm, Mantle convection currents, superheated rock flowing like molten tar 3,000 kilometers below, are pushing upward, stretching the crust until it cracks. The Mayahu incident was a warning shot, not a natural disaster, a preview, and if the pattern holds, if the African superplume continues its blowtorch work from below, the continent won't just fracture. It will birth an entirely new ocean, flooding the Rift Valley and creating a new island continent where Somalia and Eastern Africa once stood. The question isn't if, it's when. And the next crack might not wait another generation. If you want to witness the birth of an ocean, go to the Afar Triangle in Ethiopia. This isn't metaphor. The Afar Depression, also called the Danakil Depression, is the only place on Earth where a mid-ocean ridge, the kind normally hidden 2 miles beneath the Atlantic, is exposed on dry land. The ground here sits 125 meters below sea level. Temperatures regularly exceed 50 degrees Celsius. The air shimmers with sulfuric gas. And beneath your feet, the Earth's crust is so thin, only about 20 kilometers compared to the usual 35, that magma chambers sit just a few kilometers down, close enough that geologists can hear them rumbling. The Afar region is geologically unique because it's a triple junction, the Afar Triple Junction, where 3 tectonic plates meet, the Nubian, the Somalian, and the Arabian. They're all pulling away from each other simultaneously. The result is a landscape that looks like the planet is being pulled apart by invisible hands, because it is. In 2005, the Dabahu Manda Hararo rift eruption tore open a 60-kilometer fissure in just 10 days. Dereje Ayaleo, an Ethiopian geophysicist, was one of the first scientists to reach the site. He described finding pools of fresh basaltic lava still steaming, fissures wide enough to swallow trucks, and a visible ridge of new crust forming in real time. GPS measurements showed the ground had moved up to 8 meters in some locations. Satellite data confirmed what seemed impossible. The process that normally takes thousands of years at mid-ocean ridges was happening in days. Tim Wright, a geophysicist from the University of Leeds, called it the best documented rift-opening event in history. The event released approximately 2.5 cubic kilometers of magma and produced over 160 earthquakes above magnitude 3.9. What made it extraordinary wasn't just the violence, but the clarity. For the first time, scientists could observe lithospheric plates actively diverging on land, not inferred from ocean floor mapping, but directly, measurably, in real time. The Afar Triangle is essentially a wound that refuses to heal, because the forces tearing it open are stronger than anything trying to hold it together. Beneath the surface, the African Superplume, a massive blob of superheated mantle rock, is pushing upward like a blowtorch held against the crust. This creates what geologists call active rifting, where deep mantle convection drives the surface apart, as opposed to passive rifting, where plates simply drift. The evidence is everywhere: volcanic chains, geothermal vents, salt flats formed from evaporated seawater that occasionally floods in from the Red Sea. The landscape is a preview. In geological terms, the Afar Depression is an embryonic ocean. Give it another 10 million years and this desert will be underwater, a new sea separating Africa from a newly independent Somalian island. But wait, it gets stranger. The plates aren't just splitting. One of them is spinning. Between the Nubian and Somalian plates sits something that shouldn't exist: the Victoria Microplate, a roughly circular geological block about 600 kilometers across, roughly the size of Germany, that's rotating counterclockwise at approximately 0.5 degrees per million years, while simultaneously moving northeast. Discovered in the 1970s but only properly mapped in the early 2000s using GPS and seismic data, the Victoria Microplate acts like a massive stone gear caught between 2 diverging continental slabs. D. Sarah Stamps, a geodesist at Virginia Tech, led research teams that installed GPS stations across Uganda, Kenya, and Tanzania to track its motion. What they found defied simple models. While the African continent splits east-west, this microplate spins, creating a complex pattern of stress fractures, earthquakes, and volcanic activity that doesn't match standard Riftogenesis models. It's not just breaking apart, it's rotating as it breaks, like a broken piece of pottery twisting free from the hole. The mechanics behind this rotation involve something called bookshelf faulting, where multiple parallel faults allow blocks of crust to rotate relative to each other, similar to how books on a shelf can tilt when you remove the bookends. In the Victoria Microplate's case, the boundaries are defined by the Western Rift, along Lake Tanganyika, Lake Kivu, and Lake Albert, and the Eastern Rift, running through Kenya and Tanzania. As the Nubian and Somalian plates pull apart, they create differential stress, uneven forces, that cause the trapped microplate to rotate rather than simply translate. Seismic data from the 1994 Rukwa earthquake, magnitude 6.2, and the 2016 Kagera earthquake sequence revealed that the western boundary is more seismically active, suggesting that rotation creates unique fault geometries not seen in simpler two-plate rift systems. The rotation rate is slow, microscopic in human terms, but over millions of years it adds up to significant crustal deformation and explains why volcanic activity in this region doesn't align neatly with the main rift axis. What makes the Victoria microplate particularly dangerous is that its boundaries run directly beneath some of Africa's most densely populated regions and deepest lakes. Lake Kivu, Lake Tanganyika, and Lake Victoria all sit within or adjacent to the microplate's sphere of influence. The rotational stress creates pathways for magma intrusion, which means volcanic gases, particularly carbon dioxide and methane, can accumulate in lake-bottom sediments and deep water layers. The 2002 Nyiragongo eruption in the Democratic Republic of Congo, which destroyed 15% of Goma and displaced 120,000 people, occurred along the western boundary of the Victoria microplate. The lava flows reached speeds of 60 kilometers per hour, some of the fastest ever recorded. But here's what they don't tell you. Lava isn't the only threat in a rotating microplate zone. Sometimes the danger is invisible. Sometimes it's dissolved in water. And when it releases, it doesn't burn. It suffocates. The Afar Depression doesn't just host a forming ocean, it hosts alien worlds. Dalol, located in the northern Danakil Depression, holds the record for the highest average annual temperature ever recorded on Earth, 34.4 degrees Celsius, measured between 1960 and 1966. But temperature is the least remarkable thing about it. Dalol is a hydrothermal field where acidic hot springs bubble through salt deposits, creating pools of sulfuric acid with pH levels as low as 1.7, more acidic than battery acid. In 2019, a research team led by Purificación López Garcia from the French National Center for Scientific Research published findings in Nature, Ecology and Evolution confirming what the landscape already suggested. Dalol is sterile. Despite the presence of water and chemical energy, no microbial life exists in its most extreme pools. The combination of extreme acidity, high salt concentrations, high temperatures, and chaotropic magnesium compounds creates conditions so hostile that not even extremophile microbes can survive. Life, it turns out, has limits, and Dalol marks one of them. The colors at Dalol are hallucinogenic: neon yellows from sulfur deposits, rust reds from iron oxidation, emerald greens from copper salts, and pale blues from dissolved minerals. The ground is constantly shifting as new hydrothermal vents open and old ones collapse, creating ephemeral pools that appear and vanish within weeks. The hydrothermal activity is driven by the same thinned crust and mantle convection that powers the Afar Triple Junction. Magma heats groundwater that dissolves salt and minerals from ancient evaporate deposits, then forces the superheated brine to the surface, where it erupts in acid geysers and bubbling mud pots. The site is so extreme that astrobiologists use it as an analog for potentially habitable environments on Mars and Jupiter's moon Europa, places where liquid water exists, but conditions might be too harsh for life. If we can't find life in Dalol, the reasoning goes, we might not find it in similar extraterrestrial environments either. 500 kilometers south, Lake Natron in Tanzania represents a different kind of extreme. This alkaline lake, fed by mineral-rich hot springs from the Rift Valley volcanic system, has pH levels between 9 and 10.5 and temperatures that can exceed 60 degrees Celsius in shallow areas. The lake's water is so caustic that it can burn the skin and eyes of animals not adapted to it. But the most eerie characteristic is its ability to calcify and preserve animals that die in its waters. Nick Brandt, a photographer who documented the lake in 2013, found perfectly preserved birds, bats and fish whose bodies had been encrusted with sodium carbonate and other minerals, turning them into stone-like statues. The high alkalinity and unique mineral composition essentially mummify organic tissue before it can decompose, creating what locals call Medusa creatures. Animals turn to stone by the lake's chemistry. The lake appears blood red during certain seasons due to massive blooms of halophilic cyanobacteria and algae that thrive in high-salt, high-pH conditions. But these extreme environments, they're just the surface, because beneath some of these rift lakes sits a threat that's completely invisible, until it kills everyone within miles. August 21st, 1986. The villagers near Lake Nyos in Cameroon went to sleep in a world that made sense. They woke up, those who woke up, in a mass grave. Overnight, a massive cloud of carbon dioxide erupted from the lake's depths, rolling down the valleys like invisible water, displacing oxygen, suffocating everything with lungs. 1,746 people died. Over 3,500 livestock. Entire villages found with families still in their beds. No marks, no warning. Just death by asphyxiation from a lake that had been perfectly calm hours before. The gas cloud traveled up to 25 kilometers from the lake, hugging the ground because CO2 is heavier than air. Survivors described a smell like rotten eggs or gunpowder, dizziness, confusion, then waking hours later surrounded by corpses. Joseph Nquain, one of the few survivors from Nyos village itself, reported hearing a loud noise like a gunshot before losing consciousness. When he woke 14 hours later, everyone around him was dead. The lake's water had turned from blue to deep red-brown, stained with iron from the disturbed bottom sediments. What killed them was a limnic eruption, a phenomenon so rare that science had no proper framework for it until Lake Nyos forced the issue. Limnic eruptions occur in deep, stratified lakes where volcanic carbon dioxide seeps from magma chambers beneath the lake floor and dissolves into bottom water layers under immense pressure. Lake Nyos sits in an old volcanic crater 208 meters deep, and its waters are thermally stratified. Warm surface water acts as a lid, trapping cold, CO2-saturated water below. Over decades or centuries, the concentration builds until the system becomes critically unstable. Any disturbance, a landslide, an earthquake, even unusual weather patterns, can trigger what scientists call a lake overturn, where the saturated bottom water rapidly rises, depressurizes, and releases dissolved CO2 like opening a champagne bottle. At Lake Nyos, an estimated 1.6 cubic kilometers of gas erupted in a matter of hours. Michael Halbox, a French scientist who has studied the lake since 1990, installed degassing pipes that continuously vent CO2 from the lake's depths to prevent another catastrophe. But Lake Nyos isn't alone. Lake Monoun, also in Cameroon, killed 37 people in a smaller limnic eruption in 1984. And there's a far larger threat brewing. Lake Kivu, straddling the border between Rwanda and the Democratic Republic of Congo, contains an estimated 300 cubic kilometers of dissolved carbon dioxide and 60 cubic kilometers of methane, enough gas to potentially kill the 2 million people living along its shores if a full limnic eruption occurred. The lake sits directly within the Western Rift, along the boundary of the rotating Victoria Microplate, which means it's seismically active and volcanically charged. The nearby Nyiragongo volcano erupted in 2002, and its magma composition suggests it's fed by the same deep mantle source that feeds gas into the lake. Companies have begun extracting methane from Lake Kivu to use as fuel, which has the dual benefit of generating power and reducing gas saturation. A degassing project on an industrial scale. But here's the question no one wants to ask out loud. Why is there so much volcanic gas accumulating beneath these lakes in the first place? The answer lies 3,000 kilometers straight down, in a molten anomaly the size of a continent, pushing up from the core mantle boundary like a blowtorch aimed at Africa's underbelly. 3,000 kilometers beneath your feet, there's a blob, not metaphorically, literally. Seismologists call it the African Large Low Shear Velocity Province, or LLSVP, the African Superplume. It's a Texas-sized anomaly sitting at the core mantle boundary, a region where seismic waves slow down dramatically, indicating that the rock is hundreds of degrees hotter and chemically distinct from the surrounding mantle. Discovered in the 1980s through seismic tomography, essentially creating CT scans of Earth's interior using earthquake waves, the African Superplume is one of only 2 such structures on Earth, the other beneath the Pacific. Edward Garnero, a seismologist at Arizona State University, has spent decades mapping its boundaries using data from thousands of earthquakes. His research, published in Science in 2016, revealed that the superplume is not just hot, it's actively rising, feeding mantle plumes that punch through the lithosphere like blowtorches through sheet metal. The African superplume is why the continent sits higher than other landmasses of similar age. It's why East Africa has so many volcanoes, and it's why the continent is splitting in 2. The superplume works through mantle convection, the same process that drives plate tectonics globally, but concentrated and amplified. The core mantle boundary, 2,900 kilometers down, is where Earth's liquid iron outer core meets the solid silicate mantle. Heat from the core creates thermal instabilities that cause hot mantle rock to rise in massive plumes, like blobs in a lava lamp. The African superplume appears to be a megaplume, a stable structure that has existed for at least 200 million years, possibly much longer. Trond Torsvik, a geologist at the University of Oslo, traced the superplume's influence back through geological history by analyzing kimberlite pipes, vertical conduits of volcanic rock that bring diamonds from the mantle to the surface. His 2010 study in Nature showed that kimberlite eruptions across Africa clustered above the edges of the superplume over the past 320 million years, suggesting it has remained relatively stationary while continents drifted overhead. The plume's heat weakens the lithospheric plates above it, making them easier to break. It generates partial melting in the upper mantle, producing magma that feeds volcanic systems from Mount Kilimanjaro to the Virunga Mountains. And it drives the upwelling that physically pushes the Nubian and Somalian plates apart. Recent studies using helium isotope ratios from volcanic rocks in the East African Rift have confirmed that the magma feeding these volcanoes originates from the deep mantle, not the shallow crust. Helium-3, a primordial isotope trapped in the Earth's core since planetary formation, appears in unusually high concentrations in Afar region basalts, direct chemical evidence that the African superplume is tapping into ancient deep mantle reservoirs. Matthew Jackson, a geochemist at UC Santa Barbara, published findings in 2018 showing that some East African lavas contain the highest helium-3, helium-4 ratios ever measured outside of ocean island basalts like Hawaii. This isn't just a surface-level tectonic process, it's a deep Earth phenomenon, driven by heat and material that have been cycling through the planet for billions of years. But what's even more surprising is that this same deep energy system has left physical evidence on the surface, evidence that goes back way further than you'd think. Lalibela, Ethiopia, 11th century. King Gebre Meskel Lalibela ordered the construction of 11 churches carved directly from solid volcanic tuff, not built from quarried blocks, but excavated downward into living bedrock, creating monolithic structures that remain standing pieces of the mountain itself. The largest Beit Medaner measures 33 meters by 23 meters and stands 11 meters tall, carved entirely below ground level as a single block of stone. No mortar, no joints, just continuous rock shaped by human hands, using iron chisels and geological knowledge that seems impossibly advanced for the period. Archaeologists estimate it would have required removing approximately 14,000 cubic meters of volcanic rock with medieval tools. The churches sit directly in the Ethiopian highlands, part of the East African Rift's volcanic plateau, built from the same basaltic rock that the African superplume has been pushing to the surface for millions of years. The builders didn't fight the geology, they used it, carving worship spaces from stone formed by the same deep mantle convection that's currently tearing the continent apart. The rift gave them both the bedrock and the reason to dig deep, to build in stone that wouldn't shake apart when the Earth moved. But human engineering, however impressive, is nothing compared to what Earth managed on its own. In 1972, French physicist Francis Perrin was analyzing uranium samples from the Oklo mine in Gabon when he noticed something impossible. The uranium-235 isotope ratio was lower than it should be, as if the ore had already been used in a nuclear reactor. After months of investigation, the International Atomic Energy Agency confirmed the unthinkable. 16 natural nuclear fission reactors had operated in Oklo approximately 2 billion years ago, running intermittently for hundreds of thousands of years. The conditions were perfect and unrepeatable: high-grade uranium ore concentrated by groundwater in porous sandstone, natural neutron moderators from hydrogen in water, and geological stability that maintained critical mass without human intervention. These weren't just hotspots. They were self-regulating nuclear reactors that cycled on and off as groundwater flow moderated neutron activity, producing an estimated 100 kilowatts of power and fission products identical to modern reactor waste. Alexander Mashik, a geochemist at Washington University, analyzed xenon isotope ratios in the Oklo deposits and confirmed that nuclear chain reactions had occurred, complete with neutron capture and plutonium production. What connects a medieval church and a 2-billion-year-old nuclear reactor? Both are evidence of Earth as an energy system, cyclical, self-regulating, and capable of creating conditions for transformation. The Lalibela churches were carved with energy, borrowed from human muscle powered by food grown in volcanic soil, enriched by the same rift processes. The Oklo reactors ran on energy from uranium decay that began when the planet formed, concentrated by tectonic processes and hydrothermal circulation over billions of years. Both required precise geological conditions: stable bedrock at Lalibela, perfect uranium concentration, and water chemistry at Oklo. And both sit on the African continent, above the Superplume, in a region where Earth's deep energy has always been closer to the surface than anywhere else. The rift didn't just give Africa its landscape, it gave it access to geological power on timescales from centuries to eons. But all this raises a final question. If the continent has been fracturing and reforming for billions of years, what does the next cycle look like? In 2004, a team of geophysicists led by Cynthia Ebinger from Tulane University published projections in the Geological Society of America Bulletin, outlining what East Africa will look like in 10 million years if current Riftogenesis rates continue. The scenario is stark. The Somalian plate carrying Somalia, eastern Ethiopia, Kenya east of the rift, and Tanzania's coastal regions will fully detach from the Nubian plate. The Afar Triangle will flood completely as the Red Sea and Gulf of Aden break through, creating a new oceanic basin where desert currently exists. The Rift Valley will become a seaway, similar to the Red Sea but wider, eventually reaching widths of several hundred kilometers as seafloor spreading takes over from continental rifting. Madagascar, already an island, will drift further east. The Victoria Microplate's fate is less certain. It may fragment entirely or become part of the Nubian Plate's eastern margin. What is certain is that the map of Africa will be fundamentally redrawn, not by politics or borders, but by lithospheric plates responding to forces from the core mantle boundary. The timeline isn't speculation, it's extrapolation from measurable data. GPS stations across the rift zone, installed and monitored by the UNAVCO consortium and various national geological surveys, show the Nubian and Somalian plates diverging at 6 to 7 millimeters per year in the north and slightly slower rates in the south. At the Afar Triple Junction, where the Arabian plate is also pulling away, rates reach 15 to 20 millimeters per year. In 2018, Sarah Stamps and her team published refined GPS velocity models showing that the motion is accelerating in some regions, likely due to increased magmatic intrusion lubricating the rift faults. If the process continues uninterrupted, and there's no geological mechanism to stop it, the East African rift will transition from continental rifting to seafloor spreading within 5 to 10 million years. For comparison, the Atlantic Ocean opened at similar rates starting roughly 180 million years ago when Pangaea broke apart. Africa is simply repeating a process that has happened dozens of times in Earth's history. Continents don't last. They're temporary arrangements of crust riding on convection currents they can't control. The human implications depend entirely on timescale. In 10 million years, Homo sapiens will likely be extinct or evolved into something unrecognizable, so the new geography is irrelevant to us as a species. But the processes creating that future are happening now. Every earthquake in the rift zone, every volcanic eruption, every GPS-measured millimeter of plate motion is part of the same mechanical system. Cities like Nairobi, Addis Ababa, and Dar es Salaam sit inside an active continental breakup zone. The Limnic eruption threat at Lake Kivu is real and present. The seismic hazard from the Victoria Microplate's rotation affects millions today, not millions of years from now. The future map is interesting as a projection, but the real question is whether we're paying attention to what the present map is trying to tell us. The continent is not solid, it never was, and the forces that built Africa are the same forces now dismantling it, following a script written in Mantle, Convection, and tectonic shifting that started billions of years before humans existed and will continue long after we're gone. We didn't just discover that a continent is splitting. We discovered that the ground beneath our feet was never as solid as we believed. Every map, every border, every concept of geographical permanence, it's all temporary. Africa isn't unique in this. It's just the most visible example of a truth we've been avoiding. Continents are not permanent structures. They're rafts of crust floating on a convecting mantle, and when the forces below decide it's time to break them apart, no amount of human civilization, infrastructure, or belief in stability will stop it. The African superplume has been sitting at the core mantle boundary for at least 200 million years, feeding heat into the lithosphere above, creating the conditions for East Africa's volcanoes, its rift valleys, its unique geology. And now, in our lifetime, that same deep force is executing the next phase of a plan that started before dinosaurs existed. The plates are separating. The ocean is coming. And we're watching it happen in real time, measuring it in millimeters, documenting it with GPS stations and seismic arrays, while most of the world still looks at maps and sees something solid. The existential weight of this isn't in the distant future, it's in what it reveals about now. If continents break, what else are we assuming is permanent that isn't? The natural nuclear reactors ran for hundreds of thousands of years, self-regulating, cycling on and off based on groundwater flow and neutron physics, without a single human involved. Earth doesn't need us to be an energy system. It was doing complex, self-organizing processes billions of years before we showed up. The churches at Lalibela were carved from volcanic rock, created by the same mantle convection, currently tearing the continent apart. Human effort using materials provided by forces we didn't understand and still barely control. We build on geology we assume is stable, in rift valleys that are actively opening. Next to lakes filled with dissolved gas that could erupt and kill millions, we treat the ground like it's a stage, when it's actually part of the performance. The official narrative says these processes are too slow to matter, 7 millimeters per year. Who cares? But Mayahu proved that slow background processes can produce sudden, catastrophic surface events. Lake Nyos proved that invisible threats accumulate in geological silence until they don't. The Dabahu fissure proved that rift-opening events can happen in days, not millennia. The Victoria microplate is spinning between two separating continents, creating stress patterns that don't fit simple models, generating earthquakes and volcanic activity in populated regions. And the African Superplume is still there, 3,000 kilometers down, still hot, still rising, still pushing. The mechanism hasn't changed, only our ability to measure it has. Next time you look at a map of Africa, remember, you're looking at a snapshot, not a final form. The continent is in motion, the crust is breaking, and the forces doing this don't care about borders, nations, or human timescales. They operate on their own schedule, written in mantle convection and tectonic shifting, and we're just learning to read the language. This is just the first rupture. The East African Rift is one of many active tectonic boundaries reshaping the planet right now, and each one has its own deep story, its own superplume or mantle anomaly driving it from below. In upcoming videos, we'll crack open the files on other zones where the Earth is rewriting its own surface, places where the crust is colliding instead of separating, where entire mountain ranges are being built in real time, where the balance between deep forces and surface stability is just as fragile. Subscribe so you don't miss when we reveal what's happening beneath the Himalayas, or why the Pacific Ring of Fire isn't just active, it's accelerating. And turn on notifications, because these geological stories don't wait for us to be ready. The planet is moving. The only question is whether you'll be watching when the next crack appears.